Alright, so it's Niyaki Osteozone. So today we are going to have the Niyaki chemistry series, and we are focusing on equilibria and the industrial processes. So in our last session we did equilibria, we exhausted equilibria, right? So and today we are mainly focusing with the industrial processes, the applications in the principles we discussed for equilibrium, right? So industrial processes, we're only applying what we did in the previous session. So if you haven't checked on our playlist, you need to do so that we can be on the same page, right? So I believe you guys, you have already watched our previous tutorial so that you can have the full understanding on the high yield industrial processes, right? So we are providing massive topical revisions in all the science subjects, both for the O level and the A levels. So always remember to subscribe so that you'll be notified whenever we post, right? So for industrial processes, we explained in the last session that equilibria, we are dealing with reversible reactions, and we want to maximize the production of the products, concentration of the products, right? So we want to increase yield, right? So we have the conditions which affect the position of the equilibria. So we want to make sure that the position of equilibria is on the product side, right? So these conditions, we are going then to apply the conditions which favors the production of the products right? So we want to favor the production of the product. So for industrial processes, we are mainly concerned with the yield of product. We are also focusing on the cost. We want to reduce the cost, and also we want to increase the rate. So these are the aspects governing the industrial processes, right? So we want to make sure that the yield, the products, has been increased. We want to make sure that we are cutting the cost so that it can be economical benefit, and also to make sure that we're increasing the rate so that we can increase the production rate. So we are going to use compromised conditions so that we can meet all these factors together, right? So we are going to use compromised conditions. Are we together? So we are starting with the reaction, what we call the Haber process, right? We are starting with the Haber. So we have three of them. We have the Haber process, we have the contact, and then lastly we have the Oswald process, the production of ammonia, this one of sulfuric acid, then this one of nitric acid. So we are going to dissect each of these industrial processes step by step, right? So we are starting with the Haber process. So Haber process, it is the production of ammonia, right? It is the production of ammonia. So we are producing ammonia from nitrogen gas and hydrogen. So these are the raw materials, hydrogen and nitrogen. So nitrogen is obtained from fractional distillation of liquefied air. Fractional distillation of liquefied air. Right? So we're going to obtain from air, we are going to obtain nitrogen and oxygen and then other gases, right? And then the source for hydrogen, we are going to obtain hydrogen from the steam reforming processes. The reaction of steam with methane, right? So we're going to obtain hydrogen from there. And also we can obtain hydrogen from the electrolysis of water. Right? So for industrial use, we can use this one, right? And then for laboratory use, we can use this one. So these are the sources, and then these are the raw materials, right? So you must take note of the sources and the raw materials, and then the reaction for the Haber process, right? So it's nitrogen plus hydrogen to give ammonia gas, right? And then the gaseous phase, and then the gaseous phase. and we balance with reacting ratio is 1:3. For 1 mole of nitrogen, we're having 3 moles of hydrogen. You must take note of this reacting ratio. So we have the conditions. So this one is a reversible reaction, as you can see, meaning to say all the conditions are governed by what we call the Le Chatelier's principle. So we explained the Le Chatelier's principle in our previous discussion, and we say the Le Chatelier's principle, it states that if a system in equilibrium is disturbed, the equilibrium will shift to oppose the change and try to reverse it. So this is the equation for the Haber process, and we want to have the conditions which will facilitate the high yield, the product side. So this reaction is exothermic. So mostly all the industrial processes, they are exothermic reaction, right? So this is an exothermic reaction. So for us to increase the concentration of ammonia, we must have low temperature, since this one is an exothermic reaction. So we want to favor a reaction which will increase the exothermic direction. So by lowering temperature, we are promoting the exothermic reaction, where we are going to increase the production of heat to the surroundings, right? And then we are having 1 plus 3, we are having 4 moles of gaseous molecules here, and then here we are having 2, meaning to say we are going to use high pressure, right? So it's high pressure. So if you are to increase pressure according to the Le Chatelier's principle, the equilibrium position will shift in the side where we are having fewer number of gaseous molecules, right? So this is the principle, right? So this is what we discussed in our previous session. So we are going to use low temperature and high pressure. So for industrial efficiency, low temperature, it is not applicable. Why? Because the rate will reduce it, right? So from the kinetic theory of matter, temperature is directly proportional to rate. So if you are to decrease the temperature, we are also decreasing the rate of the reaction. It is not economical efficient, right? And then also to use high pressure is expensive to maintain, expensive of the cost of the pipes to maintain high pressure. It is not economical. So we are going to use compromised conditions, right? We are going to use compromised conditions. So we are going to use a pressure of 200 atms, and then we are going to use temperature of 450 degrees Celsius, and then we are going to have a catalyst, right? So the catalyst, you are going to have powdered, so it's powdered iron. It's powdered iron, not just iron, it's powdered iron. You must highlight that. Why are we using powdered iron? Because powdered iron has got an increased surface area. So the iron is powdered, meaning to say we have many contact points where the gases would absorption of the gases. So we explained this in reaction kinetics, where we did catalysis, right? Are we together? So we are reacting hydrogen and nitrogen. So these two will absorb on these surfaces of iron, and then they will react in this pathway. So this direction we have high activation energy. So we are going to use this direction where we are having reduced activation energy. So we define the catalyst as a chemical substance which increases the rate of a reaction by providing an alternative route with lower activation energy. So this is the route with low activation energy to produce required ammonia, right? And then these are the products, these are the conditions, these are the conditions for the Haber process, right? So we are simply going to have the flow chart, right, for the Haber process, right? So we are having this one plus this one is for hydrogen, right? And then this one is for nitrogen, and then we say the source from air, and then the source here from natural gas, which is methane, natural gas, and then they are going to react in the volume, in the ratio 1:3 by volume, right? And then we are going to have the conditions here, right? So this is the direction, and then this is the direction, and then we are going to have the conditions here. So we said 450 degrees, and then 200 atms, and then powdered iron, right? And then we are going to produce our ammonia here. So it's NH3, right? NH3. So this is the produced ammonia, right? And then ammonia is produced as a gas, so we're going to have the liquefaction of ammonia to have liquid ammonia. Are we together, right? So this reaction, we have a 15% yield. So meaning to say we are going to have recycling of the reactants again. So we're going to have 15% yield, and then we have recycling of unreacted. That's it, right? Are we together? So this is the overview of the Haber process, and then we go on to explain the uses of ammonia. So for the uses of ammonia, we're going to have the manufacturing of fertilizers. So it's fertilizer production, right? And then fertilizers like ammonium nitrate and etc. for agricultural boosting, right? So we are going to have fertilizers production, and also the production of explosives, right? And also used in the manufacturing of nitric acid, right? And cleaning agent, refrigeration, and for pharmaceuticals and dyes, and then for water treatment. So we must know the uses of ammonia. So for the Haber process, what you need to do is to be able to explain why we use these conditions. Why? Because from the reaction, we know that we are supposed to use low temperature and high pressure for us to favor the production of ammonia, but we are using 450, which is not a low pressure, and we are using 200, which is also not a high pressure. You must be able to explain why we are using these conditions, right? Why we are using the compromised conditions. Are we together? So we are done with the Haber process, and we are now moving on to the conduct process, right? So the conduct process, it is the production of sulfuric acid, right? So this is the conduct process. We want to produce sulfuric acid, right? So we are starting with the production of sulfur dioxide. So the first, it is the production of sulfur dioxide from the oxidation of sulfur, right? So we are going to roast sulfur containing compounds, what you call the sulfides, the metal sulfide. So we have what you call the iron pyrites, which is iron sulfide, right? It's iron sulfide, right? So we are simply going to react sulfur plus oxygen, right, for small scale to have sulfur dioxide, and then we are going to roast the iron pyrites plus oxygen to give iron 3 oxide plus sulfur dioxide. And then to balance this equation, we're simply going to have a 4 here, then a 2 there, then we can have 11 here, then an 8 there, and then the equation is balanced. So this is the first step 1, the production of sulfur dioxide. And then we go on to the next step. That's where the conduct process is, right? So we are having step number 2, where we are having the produced sulfur dioxide oxidized to give sulfur trioxide. And then this reaction is a reversible reaction. So we said the industrial processes, we are having reversible reactions which are exothermic in the energetical nature, right? So to balance this equation, we are simply going to have a 2 here and to have a 2 there, right? So this is the equation. So this reaction is an exothermic reaction, meaning to say it is producing heat to the surrounding. So for us to increase the concentration of sulfur dioxide, we are going to use compromised conditions. So according to Le Chatelier's principle, we were supposed to use a low temperature. So this forward reaction is producing heat. So if we were to lower the temperature, we are favoring the exothermic direction. The reaction will move in the exothermic direction, which is the forward reaction. Are we together? So this is what you are supposed to know, right? You're supposed to know this by heart. Are we together? So we are supposed to lower the temperature. And then in terms of pressure, we are supposed so here we're having 3, so 1, 2 plus 1, having 3, and then here we're having 2. So for us to increase the forward reaction, the concentration of the product, the yield, we want to use a pressure which will favor this forward direction. So we are going to use high pressure so that the equilibrium position will shift in the direction where we are having fewer number of gas molecules, which is the product side. Are we together? So we are using a compromised conditions. We are using a temperature of 450 degrees Celsius, a pressure of about 1 to 2 atmospheres, and then we are going to use a catalyst, which is vanadium pentoxide, right? So this is our catalyst. These are the conditions for the conduct process. Are we together? So you must know the conditions by heart and should be able to explain why we are using these compromised conditions. Are we together? And then you should also be able to explain the conditions which favor the production of the products with respect to the Le Chatelier's principle, right? And then the next, we have produced the sulfur trioxide. So we have this reaction. You must take note of this one. So it's sulfur trioxide plus water to give sulfuric acid. So this reaction, from the understanding we have from periodicity, the hydration of sulfur trioxide will give us sulfuric acid, right? So we avoid this reaction. We must avoid this reaction in the conductive process. Why? Because this reaction is highly exothermic, right? It is highly exothermic. So to an extent that we are going to produce the mist of sulfuric acid. So the mists are difficult to condense, right? They are difficult to condense. So you must take note of that. Why we are avoiding this reaction, the direct hydration of sulfur trioxide to give sulfuric acid, because it is going to produce the fumes or the mist of sulfuric acid which are difficult to condense, right? So you must avoid this direct method. We are going to absorb sulfur trioxide in already made concentrated sulfuric acid. Already made concentrated sulfuric acid. So we have already made concentrated sulfuric acid by this pathway, right, which is there for this absorption process, right? So we're going to have sulfur trioxide absorbed into sulfuric acid to give what you call oleum. So this is oleum, right? So this is oleum. So to have sulfuric acid, we then dilute this oleum, right? So we are having oleum diluted by water to give sulfuric acid. Are we together? So you must know these stages, and you must always be able to explain why we avoid this direct hydration of sulfur trioxide. So this is the overview for the conduct process. Are we together? So you must know the equations, and you must be able to explain with respect to the Le Chatelier's principle why we are using these conditions, right? And then we can now discuss the uses of sulfuric acid, right? So sulfuric acid can also be used in the manufacturing of fertilizers, right, like ammonium sulfate. So we can have ammonium sulfate, right, and can be used as an electrolyte in the battery. So we have the lead acid accumulator. So we explain this in the electrolysis, right? Electrolytic cells, electric cells, right? And we can also use sulfuric acid in the manufacturing of detergents, paints, plastics, explosives, and synthetic fibers. Are we together? And then we are having we can also have petroleum refining, and we can also have metal processing. Are we together? And lastly, sulfuric acid can be used in laboratory procedures. Right? So these are the uses of sulfuric acid, and this is the overview for the conduct process. And also remember that for the conduct process, we are having a 99.5% yield. 99.5% yield, right? So this is the yield for the Haber process, for the conduct process, and then the yield for the Haber process, we said is 15%. So you must understand these industrial processes by heart. And then lastly, we are moving to the Ostwald process, right? So we are now diving into the Ostwald process. So the Oswald process can also be called the catalytic oxidation of ammonia. So it is the catalytic oxidation of ammonia, right? So we are having the oxidation of ammonia, right? So this is self-explanatory. So the first reaction, we are going to have the oxidation of ammonia. It's ammonia plus oxygen to give nitrogen monoxide or nitric oxide plus water. And to balance this reaction, we are going to have 4 moles here, and then we are going to have 4 moles there, and then we are going to have 5 here, and then we are going to have 6 there. So the conditions for this reaction, we are going to have temperature of about 800 to 900 degrees Celsius, and then we are going to have a pressure of about 8 to 10 atm. And then for the catalyst, we are going to use platinum rhodinum, right? So it's platinum rhodinum. So you must know the conditions by heart. And then also remember that this one is an exothermic reaction, right? And then we go on to the next stage. So the next stage, we are going to have the oxidation of nitric oxide to give nitrogen dioxide, right? So this is a reversible reaction, which is exothermic in nature, right? And to balance this reaction, we're going to have 2 here, and then we're going to have a 2 there, right? So next we are going to have the oxidation of this nitric oxide into nitrogen dioxide, right? So this one is the only reversible reaction in the Oswald process, right? So to balance this equation, we simply need to have a 2 here, and then to have a 2 there, and it is also an exothermic reaction. Are we together? So this one is the only reversible reaction in the Oswald process. You must know this by heart, right? And then we go on to the next step, where we are having the absorption of this produced nitrogen dioxide in water, right? So we are having nitrogen dioxide plus water to give nitric acid plus nitrogen monoxide. So the produced nitric oxide is then recycled again, right? So it is then recycled again. Also remember that this reaction is not reversible. Why? Because nitrogen dioxide is highly reactive with water, so there are no possibilities of a backward reaction. Are we together? So this is what you must understand for the Oswald process. And then this one is our nitric acid. And to balance this equation, we can have a 3 here, and then we can have 2 there, and the equation is now balanced. So this is the general overview for the Oswald process, and you should be able to explain why we are using these conditions and to state the conditions for each and every of these industrial processes. And then for the uses of nitric acid, we can use nitric acid in the production of fertilizer. So these industrial processes can be used in the production of fertilizers. And then we can use it in the nitration of benzene. So we are going to understand this when we are doing A-level chemistry, organic chemistry, right? So this is manufacturing of explosive. And then we are having metal industry. And then we are going to have the manufacturing of dyes and plastics and drugs. Manufacturing of dyes, plastics and drugs, right? And then we can also have the laboratory use in the laboratory procedures, right? So use in the labs, right? And then what else we are done for these industrial processes, right? So what you must understand regarding the industrial process is these 3 crucial terms. We want to increase the yield, the concentration of the product, we want to cut the cost, and we want to increase the rate of the reaction. We want to make sure that the reaction is occurring at a faster rate. So this is what you must know for these industrial processes, right? And we are done. So always remember to subscribe, to like, to comment, and to share.